So the three objectives for 6.1 are to compare the relative momentum of two objects, to identify when there's a change in momentum, and then apply what's called the momentum impulse theory. And the momentum impulse theory, we'll see, is very useful in class. And yes, last year Helen named it MIT, momentum impulse theory. So you're welcome to remember MIT for that, okay, momentum impulse theory. At the first definition of momentum. So momentum is a quantity that describes the product of the mass and velocity of an object. That's all it is. Momentum is defined by the letter P, lowercase p. What was uppercase P from last chapter? Power. Okay, not to be misconstrued with momentum. Momentum is lowercase p. Lowercase p. Without looking up online, anybody have any idea why it may be called P for momentum? Anyone have any idea why it would be called P for momentum? Because they ran out of other variables, right? How about this one? I will give a point on a test. One bonus point on a test. Okay, now, if you can come up with it, listen. If you can come up with it, and it's the first person to send me an email after school, though, not during school hours. Deal? If you forget, you forget. But I don't want you emailing me during school while you're in the other classes and stuff. So the first person to email me after school, so as soon as the bell rings, if you know what it is you want to email me, first person I'll give a bonus point in the next test. For why momentum is represented by the letter P. Okay? Alright. Now, it's the product of mass times velocity. Mass is measured in kilograms. Velocity is measured in meters per second. Kilograms, meters per second. There's no simplified unit for that. So the units of momentum are kilogram, meter per second. Again, there's no simplified unit. So the units are literally kilogram, meter per second. Those are going to be our units for momentum in this chapter. Okay, keep that in the back of your mind. Say again? P represents the variable for momentum. P means momentum. Okay, momentum equals mass times velocity. Right? Okay. Let me see what else I want to go over for this. Alright, so for the, I want to see if I have another slide. Momentum impulse theory, what I'd like to do is take a quick look at the derivation of it. Okay, if we look at the derivation of it. Now, if we write an equation to start and look at our momentum and the rate of change in momentum. Let's start by writing this. Let's write delta P over time. This is the rate of change of the momentum of an object. Okay, of the momentum of an object. Now, a moment ago we said that momentum equals mass times velocity. So that would equal mass times velocity over time. So again, this was momentum equals mv. I'm just dividing both sides by time. I'm dividing both sides by time. What do you notice when you have a v over t? What does v over t really stand for? Please raise your hand. What does v over t stand for? Acceleration. Very good. Good memory of your equations. So this is really, agreed? Again, v over t is really acceleration. So we can replace that v over t with the variable a instead of having v over t on the right-hand side there. Which leaves us with delta p over t equals ma. But what was Newton's law that told us about ma? What was ma really, Reese?
Force.
Force, good. The net force on an object. So really what this tells us is that the change in momentum over time is equal to the net force on an object.
So we've been solving for this.
So what this is going to do is it's going to enable us to relate force and momentum. That's what it's going to do. It's going to come up with a relationship. What do you mean?
They're not going to be the same numbers. Like we found F net in other problems, but that's not.
Yeah, so if we found F net on an object, we can use that F net in this equation. Yep. So Ev is noticing that this is a linking variable. Okay, if we found F net, the net force acting on an object, we can plug that in here to determine the amount of momentum that has changed. What does delta mean again? Change, right? The change in momentum. So our momentum impulse theory is simply this right here. Now, a lot of books solve for delta P, and we can do that, and that's fine. And we could say that the momentum equals the net force times the time period acting on the object. Okay? So again, the momentum impulse theory here is that the change in an object's momentum is really proportional to the force applied. The proportionality constant happens to be time. Okay, happens to be time here. Let's take a look at the first example. So we've got two formulas. Again, we've got delta P equals F times T, and then we've got the beginning formula that P equals mv. So depending on what we have in a problem, we have to choose one of those two formulas. Remember how for work we had like 3 different formulas there? Same idea. Again, formula number 1, P equals mv. Formula number 2, change in momentum equals the net force times the time period. On your formula sheet, I write this as F times T. I drop the net there, just to give you a heads up when you see it on your formula sheet. So example 1 says, what velocity must a bullet with a mass of 4 grams have in order to have the same momentum as a bowling ball with a mass of 6 kilograms that's traveling with a velocity of 8 meters per second? Okay, so we want to know if we have a bullet with a simple mass of 4 grams and then a bowling ball with a mass of 6 kilograms rather. We have the bowling ball's velocity. We want to know what velocity does the bullet need so that they have the same momentum. Now, before we come up with an answer, what can you tell me about the relative velocity? Will it be greater than, less than, or equal to the velocity of the bowling ball in order for them to have the same momentum?
Well, the bullet's going to have a greater velocity than P.
Why?
Because in order for a bullet, or like a smaller object with a smaller mass, to have the same amount of momentum or force,
Good.
You have to have a greater velocity and vice versa.
Absolutely right. Same analogy. This is analogous to the football player we looked at a minute ago. A smaller football player is only able to run through somebody who's trying to tackle them that's bigger if they're, I'm talking about an actual collision, not like deking someone out, right? So actually run through them if they have a higher velocity, because their mass is smaller. So running backs with higher velocities are able to do that because they can create higher momentum than the linebacker that may be either A, standing still and waiting to tackle, or B, just have a larger mass but not running as fast. So when you see people going for tackles when they're coming at somebody and they're waiting, this person is running full speed, this person is waiting. Sure, they have a lot of strength in their legs, but sometimes that running back can actually overpower the person tackling them because the product of their mass and velocity, okay, can overcome the amount of force that this person can resist with. Now, we clearly have a small mass here for the bullet. What should we do with that mass to start the problem? What should we do? Convert it into what? So the mass of object 1 is 4 grams. In kilograms, what is that? Good, 0.004. The velocity of the object is unknown. The mass of the second object is much greater, and it's already in kilograms. And the velocity of the bowling ball is 8 meters per second. Okay, Mike?
Can you just say like a proportion?
Yeah, you absolutely can, and you're going to see in a moment that the result of this does produce a proportion.
But do you have to use if a question like this is on the test, do we have to use actual formulas, or can we just go straight?
Well, you need to know that the proportion is going to be at first a little misleading. It's not going to be. Tell me what you would set up as your proportion like.
I was going to do. I'm not really good at the order, but I guess we could do x over 0.004. Alright, x over 0.004 equals 8 over 6, or vice versa, I'm not really sure.
Okay, and that's the reason I wanted to ask you, not to call you out, but because it's difficult to figure out which way the proportion would be without actually knowing the formula. Let's write the formula and you'll see the proportion come out as a result. So we want these momentums to be equal to each other, right? So we could technically find momentum 1, find momentum 2, set them equal. Well, it's the same thing as just doing this. Momentum 1 is that. Momentum 2 is this. Agreed? A minute ago, we defined momentum as the product of mass and velocity. So the momentum of the first object is m1, v1. The momentum of the second object is m2, v2. So we want those momenta to be equal to each other, so we set them equal. Now, what are we trying to solve for? v1. So let's divide by m1 on both sides. And that gives us v1. Now, Mike, if we had done a proportion, we have to divide both sides by v2 now, and it would get v1 over v2 equals m2 over m1. So they would be switched. And that's the part that a lot of people forget with the proportion. So I would recommend just setting up the equation here. It just makes it a little easier. Okay? So go ahead and solve for v1 by multiplying m2 v2 over m1. Again, go ahead and complete this part here by multiplying and dividing, please. And your units need to match up and make sense. And you'll see that they'll cancel out. The kilogram units cancel, leaving behind units of meters per second, which is what we're looking for because we're looking for velocity. 6 times 8 is easy, that's 48. And 48 divided by 4 is going to give us 12. So this should be what, 12,000? Right, 12,000?
Yeah.
Okay, 12,000 meters per second. Our answer will be 12,000 meters per second. Say again? And that's the thing about this problem. If we were not asked to find the actual momentum, there's no need to do it. We could find the momentum, just take 12,000 times 0.004 for the bullet, and then take 6 times 8 for the other one. The momentum is 48, right? Because 6 times 8 is just 48. So the bowling ball would be the easy way to find the momentum. It's got a mass of 6 kilograms, a velocity of 8 meters per second. 6 times 8 is 48. So the momentum is 48 in this problem, but we never even had to find that. It didn't ask for the momentum. It just said find the velocity. So by setting up this equation, m1 v1 equals m2 v2, we already set the momenta equal to each other. And then we just solve for v1. Again, if the problem says what is the momentum, then yes, go ahead and do m times v. Okay, go ahead and do m times v if so. Let's take a quick look at example 2. A 1,500 kilogram car moving with a velocity of 20 meters per second east collides with a tree. Okay, and comes to rest in 2 seconds. Find the force exerted on the car. Now, right away, you're hearing mass, velocity, force, time period. So we're probably not going to use momentum equals mv. What are we going to use this time? Yeah, the delta P, the momentum impulse theory. So let's list our givens. Mass is 1,500 kilograms. It's the mass of the car. The velocity of the car initially is what? The final velocity of the car is? Why is it 0? You're right. Good, comes to rest. The time period undergone during collision is 2 seconds. So the car hits the tree, the front end of the car starts to compress. You ever seen a car accident? You see the front end buckle in. It compresses until the car eventually stops moving, and then it stops after 2 seconds. And we are looking for the force exerted on the car during the collision. That's what we're looking for. Okay, we'll pick up with this tomorrow in class. We know the mass, we know the initial and the final velocity. But what can we do for delta P? Any ideas? Nick?
mv2 times, m times vf minus m times vi.
How come you can say that, Nick?
Because p is defined as m times v, and we have 2 velocities, so the mass is constant, so we can do that.
Absolutely right. Very good. So notice it's a delta P. What does delta mean, Mike? Change. So if I'm looking for change, I'm really replacing this with m times v, but I'm going to put a delta v there to show that it's a change in velocity. Remember that momentum is defined as m times v, but here we have m times delta v. So this becomes m times the quantity vf minus vi equals f times t. And this is where Nick came up with this line right here. mvf minus mvi. Okay, so that's what we're going to end up using. So this problem can be a little bit difficult at first because it seems as if we don't have a delta p. But we indeed do have delta p. It's m delta v, which is m times the quantity vf minus vi, mvf minus mvi. But what's the easy part about this? What can I cross off?
Oh, V.
Yeah, because it's,
0.
yeah, it comes to rest. So this is gone. Be careful there. You can only cross off the m if it's on both sides of the equation in all terms. But it's not on the right-hand side. Okay? So in this problem now, all we have to do is solve. What do you notice? What do you notice? And not number, but just idea. What do you notice about this? Anybody see something?
There's the negative sign.
Yeah, it's a negative sign. So if I divide by time, right, divide by t, on both sides, divide by t, gets rid of it. So what does that do? What does that tell me, that negative sign? What? No, come on.
The forces.
Yeah, it's going the opposite way.
Yeah, so the car is going this way, isn't it? East. Which way is the tree going to push?
West.
West. If the tree doesn't push west, that car's not going to stop. Think about it. I have a car and I'm driving down the road, and if I push and I hit the tree, if the tree doesn't push back this way, I will not come to rest. But the problem says I come to rest. Therefore, the tree must push west. So the tree's force is going to be negative. The answer we're going to get has got to be negative because the tree is pushing back against motion. What are my units going to be for my answer? Yeah, newtons. Why newtons? Because it's a force, good, or because look at the units at the top. This becomes kilogram meters per second squared. They don't cancel, be careful. I know it's misleading because this looks like it's in the numerator, but it's not, right? It's in the denominator?
Yeah.
Because it's below the fraction line. So this seconds, dimensionally, really belong down here, which makes it kilogram times meter per second or second squared. And that's what the definition of a Newton is. Okay? So a Newton, if you remember, is defined as kilogram meters per second squared. So dimensionally, we can see that it's definitely newtons. You can do this in your head. You don't need a calculator. What's 20 divided by 2? 10 times 1,500 is 15,000. Okay, short, you can definitely use your calculator, and I don't mind that. But I'm just telling you that when you see a relationship with zeros, take advantage of it, please. Any questions on this one? I know we started yesterday, so you might have to think back. You need a glass of water? You want to wake up a little?
No,
Okay. If you do, I don't mind. I wasn't being sarcastic. I'm being honest. Okay, let's see. So we've got a soccer ball, and it's kicked into a wall. And it says, God bless you, it says it's kicked to the right with a velocity of 9 meters per second, and it bounces off the wall. The wall exerts a force on the ball, obviously, for it to bounce back, of 42.5 newtons. And it takes a time period of only 1/5 of a second. And think about that, that's logical. The ball hits the wall, it rebounds pretty quickly, doesn't it? So the time duration that the ball is in contact with the wall is only 0.2 seconds. So that number is reasonable. We want to determine the velocity of the ball after it hits the wall. So the return velocity that it's going to come back at you with. Okay? So how fast does the ball come back off the wall with? Now, in this problem we have to use momentum impulse theory, but it's a little bit trickier, right? Because we have a different object. It's coming back. It's not coming to rest. So there's a small variation from this problem and between this problem and the last problem. What is it? What's the only variation? This is where physics becomes a little bit tricky. And not tricky, but intuitive. Use your analogous situations. The last situation is the same as this. There's one difference now. One difference. What do we... Well, we don't have it because that's what we're trying to find. Remember the last problem? What was the VF? Because the car came to rest, didn't it, after it hit the tree? But now the soccer ball doesn't stop. Kick a soccer ball into the wall. Is it going to stop? It's going to come back off the wall, right? It rebounds. Whereas a car that hits a tree is going to wrap itself around the tree and come to rest and probably stay at the tree. It's not going to come back off the tree. It usually stops. So here, the only difference is that we're looking for VF. And we've got F in this problem. In the last problem, we didn't have F. Okay, so let's list our givens, and we'll see that it's the same exact problem with that one change. Mass? Okay, Phil.
So we could just put it down to the same equation.
In the end, we're going to see the same equation. That's what we're going to notice. Very good. Mass is? Okay, 1/2 kilogram. The initial velocity? We're looking for final velocity. The F net? Be careful.
That's the net.
What's F net?
Is it not just the force of the wall?
You have to find the forces of the ball too, right?
I'm 7
I kick a soccer ball to the right. Which way does the wall push?
Pushes back to the left.
So the force is negative 42.5 newtons. Okay, negative 42.5 newtons. And the time period is obviously 0.2 seconds.
Isn't the F net all the forces?
All the forces that act on the ball during the problem. Now, once we kick the ball, the problem has started. Okay, now we're looking at the problem. The only force acting on the ball then is the wall pushing back. Again, we're assuming there's no air resistance, right? There's no force of drag on the ball. So let's go ahead and look at this problem. We start with our same formula, momentum impulse theory. Delta P equals equals F delta T. F times T. Come on. There we go. But delta P, again, is defined, as Nick told us a moment ago, as the change in mass times velocity. But since mass is constant, it's just mass times change in velocity. Now, in this problem, we can't just drop off VF. In the last problem, we were able to say, well, VF doesn't matter. We'll cross it off because the final velocity is 0. It comes to rest. But clearly here, it doesn't come to rest. So what do we do here? What do we want to solve for? What are we looking for?
You add MVI.
Yeah, let's add MVI over and then divide by M. So let's move this over by adding and then divide by M to get VF by itself. So it's F times T plus MVI all over M. It's our generic solution. What do we get for a number? Let's go ahead and plug in. What kind of an answer do you expect? What is it? Why? Because it's what? Yeah, it's coming back off the wall. If it went toward the wall with a positive velocity, it comes back off the wall with a negative velocity. It's the opposite direction. So you can expect a negative, and you can clearly see that here we're multiplying these two, and here we're multiplying these two. We will end up getting a negative here that supersedes this positive, right? It's greater than the positive component of that numerator. What do I get?
I got negative 7.8.
Negative 7.8. Agree, disagree? You got negative 7.8. What did others get?
I got -8.
I got negative 8 also, exactly. Did you use 9.81 by accident or something else? Is that possible?
I'll do it again.
Okay. I got negative 8. That's all right. Typo, right? Somewhere along the way. So the rebounded velocity is negative 8 meters per second. Now, again, intuition. What about this number makes sense? There are two things about it. We already stated one of them. Two things about this number that make sense. Nick?
Yeah, I was gonna say it's less than the initial velocity,
Which was what?
which is 9,
Why is it less than?
because it's bouncing back from walls to wall and absorbs all the energy, so.
Absolutely right. Very good.
Is it 0.8 or
8. Check your decimals along the way. Did you put a decimal here? Did you put a decimal here? Your mass has to be 0.5. You might have just put 5 for mass on the bottom. Is that right? Yeah. So the value is negative because it bounces off the wall, comes backward, and it's less than the value of 9, absolute value-wise, right? 8 is less than 9 because you're losing some energy when the ball hits the wall. Anybody ever see this before? Have you ever looked at a basketball or soccer ball on a high-speed camera? Yeah. Absolutely right, Mike. It deforms like a spring. That's why, remember when I talked about springs last chapter, I was saying how everything in the world can really be modeled by springs. Everything can be modeled as a spring. Everything can be modeled as a spring. It's kind of amazing to think about. A soccer ball, it hits the wall, it kind of compresses a little bit, and then it expands, and that's what pushes it back off the wall. It's like a spring. It's no different. Okay, it's based on the pressure inside of the ball that determines how much it will compress or expand. So it's losing energy to that possible deformation and then coming back off the wall. It's losing energy to change its shape. That's why the velocity is going to be a little bit less on the way back. Does that make sense so far? All right. Let's take a look at example 4. At the end of these problems, when I make these statements, when are these going to come up on tests? Yeah. Multiple choice or a short answer, right? These are the kind of questions you can expect. Why does the answer make sense, right? Or what kind of an answer are you going to get? Negative, because it's coming off the wall. It's less than the original velocity because you're losing energy to that collision in the wall. Okay? All right. Example 4. Can I get someone to read for us nice and loud? Read for us? Awesome. Thanks, Maria. Number 4, nice and loud. I know you like to read. You don't mind.
A 2,000-kilogram car traveling to east slows down uniformly for 25 meters per second to 10 meters per second. A. How long does it take the car to do this if the force on the car is 750 newton? B. How far does the car travel during the deceleration?
Okay. So we're looking for the time period and the distance. The time period and the distance. Now, where is the 750 Newton force coming from? Friction. Good. Friction. Specifically now. What kind of friction? How does it come about? Where does friction come from in this problem? Okay, the street. Part of it is the street, absolutely. You're absolutely right, the friction.
I mean, it's from the force of gravity pushing down, and the normal force pushing up, and then like.
Okay, so the normal force does cause friction, you're right, because it's proportional.
Comes from the west.
What else?
Friction comes from the west opposing the motion of the car.
So to be negative, good. But I mean specifically, the person in the car, how do they create friction? What do they do? What?
They step on the brake.
Step on the brakes, right? So where's the 750 Newton force coming from? Well, how does a car slow down? They hit the brakes. So the person hits the brakes engage on the car. It's your brake pad. Your brake pad slowly deteriorates when it slows down the car against the wheel. It compresses. It slows the wheel's motion down, which then acts to slow down the actual car. Now, if you slammed on the brakes and it caused your wheels to lock and you started skidding, then it's all the friction in the road. But we know that cars don't do that. What do cars have in them? It causes them to not lock the wheels. It's called ABS.
Isn't it like click a lot?
Yeah.
So that it breaks and lets go and breaks less.
What is that called? Absolutely right. Absolutely
I
right,
don't know
Reese.
what it's called. I just know cars have that feature.
It's called an anti-lock brake system, ABS, and the reason being is this. A car, when the brakes are engaged, naturally, if you push all the way down, you're going to cause the tires to lock up, and they'll stop, and then you'll start to slide along the road. But when a car slides on stopped tires, if it were moving, you lose control of the car. You would start to fishtail and the car would go off the road. What a car does if you slam on the brakes is it causes the brakes to pump on itself. It's called an anti-lock brake system. And it causes your car to engage and disengage the brake pad. And that causes the car to slow down, but in a motion that doesn't allow you to lose control of the car. It helps you maintain control of the car. This happened to me one time when I was driving, and I've never had it happen once ever again. And it only happens if you need to literally slam on the brakes. And I was driving with my younger brother, and we were driving and trying to find some place, and it was actually in like a snowstorm. And, what is this funny? And we're driving in a snowstorm, and it was pretty bad to the point where I was like, you know what a whiteout is?
Yeah.
When you can't see in front of you because the snow is so bad, and it was one of those situations. And I happened to be on a road that was paved very well, thank God, because if it wasn't, I would have ended up causing an accident.
So you killed someone.
So, no. So I'm driving down the road, and because of the fact that it was like you couldn't see within like 10 feet in front of you, I was only going like 25 miles an hour. But out of nowhere, a car stopped in the middle of the road. It wasn't even a red light. They had just stopped for some reason, who knows why. And I had to slam on the brakes. And that's what I noticed, and I never experienced this before. And you won't experience it unless you ever really hit the brakes. The pedal would literally do this. Okay? It actually like pumped itself. And I'm like, I freaked out. I didn't know what was going on. And that was the first time I ever realized it. So good to know for you guys. If you ever slam on the brake and you feel the brake doing this, it actually does it for a reason, so you don't lock the wheels and then start skidding on the road. It causes your tires to slow in a different manner.
Was your foot
Yeah, so you hit the brakes and it will literally push up and down your foot. I kept pushing down the brake thinking it wasn't working. And I'm like pushing, but the anti-lock brake system is stronger than my foot. So I was still pushing and it wasn't overpowering it, so it was doing this to slow down the car. Okay, it's a fun fact. Yes. It's crazy because no. He was nervous because both of us, we didn't see the car. It came out of nowhere. This car just was stopped in the middle of the road and we had to slam on our brakes.
And I was in the little.
Yeah, but you're going slow.
Thankfully, yeah, because it was a snowstorm. I was only doing it was like 20 miles an hour. Okay, and because of the it's weird when you can see things in your peripheral. They're like because of the snowstorm, okay, that's why I was going so slow, and thankfully it was okay. So, I'll give you another, not story, but just, it's crazy the way things work out. I've never gotten into a car accident. And so about 4 years ago, my grandma passed away. And she passed away, and we didn't think she was going to die. Nobody thought she was going to die. She went in for a regular surgery. She went in. We didn't think she was going to die. She went in for a surgery. My grandma.
Oh, like during surgery?
Sorry, yeah. So she went in for a surgery on her heart.
And now you're locked in charge of her house.
And she came out of the surgery but didn't wake up.
Oh, I'm sorry.
There was a problem with the surgery. Thank you. It was a long time ago, so it's not like new, but it still is something that's difficult. So it was during Christmas time. She went in on 3 days before Thanksgiving. The surgery was the day after Thanksgiving, so we spent Thanksgiving there, had dinner in the room with her, and then she went in for surgery the day after Thanksgiving. She ended up dying on Christmas Eve, officially. But in the time period between Thanksgiving and Christmas, myself and my brothers, this is going to sound crazy, got into 3 accidents, or 3 possible accidents. One was that situation with me. Another time, my brother got into an accident on a highway and his car flipped like 5 times. He was doing like 60 miles an hour. And he and the 3 people in the car got nothing done. They were completely unscratched. One of them wasn't wearing a seatbelt. Somehow made it out completely fine. Okay? Unbelievable. My other younger brother, this is crazy to think about. My other younger brother was driving on a side street and lost control of his car in the snow and crashed into a fence. Was completely unharmed. There was nobody on the side of the road. Didn't harm anybody. And this all happened while she was in a coma. Isn't that crazy to think about? Right? And we were like thinking about that the whole time, like, oh my God, that's unbelievable. None of us ever got into an accident, and when this all happened was when she was in a coma and none of us got hurt. And like from this day on, my older brother had something happen to him that's a little different. I'm not going to go into detail, but somehow he's okay, which we didn't think he'd be okay from. So it's kind of crazy to think about this kind of stuff, right? But that's a side note. Anyway, let's get back to the problem. So the problem wants to know how long it takes for the car to slow down. You can, yes. Let's go ahead and list our givens here. So the mass of the car is 2,000 kilograms. The car slows down. Now, what's the initial velocity in this problem?
0.
Initial.
25.
Okay, and it doesn't come to rest though. So be careful with the 0. Yeah, it's 10 here. Good. Okay, so the car slows down from 25 to 10 meters per second. It takes, we don't know how long. We know the force applied on the car is going to be in what direction? Negative. Good. So we want to find the time period that it takes. So again, what are we going to use? Yeah. Delta P equals force times time, or the momentum impulse theory. So let's go ahead and list, instead of delta P, what are we going to put? Always VF first.
M delta V.
Yeah. Very good. M delta V. So MVF minus MVI. And we're trying to find the time. So again, it's the same kind of problem. We'll divide by force. Now in this problem, because you're not finding VF or VI, we could stay with what Scott said and just write M delta V, because delta V is obvious. What's delta V? Negative 15, right? We're going to have 10 minus 25. Okay, so you could write that as M delta V and just put in for delta V, or you can write it this way. It doesn't matter. Either way is fine. What do you notice? Negative, negative becomes a? And that has to make sense. Positive time there, okay? So if you switched up your VI and VF and you had a negative time, that should indicate to you, wait, let me check. What did I do wrong? Oh, my force is acting against motion, so my force happens to be negative. Okay? Anybody want to give me an answer when they get it?
Not 40.
40 seconds. Very good. 40 seconds. So if you were driving and the braking force were at 750 newtons, 40 seconds to come to rest. So, realistically speaking, do you think the braking force is only 750 newtons? No, it's probably a lot higher than 750. So, hypothetically speaking, try a number like 3,000 in your denominator. Try a number like 3,000 in your denominator and see what you get for a time now.
Negative 2,000.
Yeah, sorry, negative 3,000.
10.
Yeah, 10 seconds you should get. A quarter of the time. Because 3,000 is 4 times 750. So if the force of the brakes can be quadrupled, it will cut my time in 4 to brake. Okay, and it takes, we're talking about, let's see, 25 meters per second to 10 meters per second.
How fast is miles per hour?
That's what I was just going to ask. Can somebody convert that real quick? Just go to Google. Or I can even, actually I can do it. Let me do it on this. Hold on. I forgot I can do this. I can add a browser. I haven't used it much this year, but watch. I can throw a browser in here and just go to Google. It's pretty sweet.
What is this?
In Notability or in Explain Everything, I can record with a browser in here. I forgot I can do this, and I haven't used it much this year.
Pretty amazing.
So we're going to go, what, 25 meters per second, right? Look at the first thing that comes up. 25 burgers.
That's when you type in "why do I" or like something like
Oh,
that.
gosh,
You
I
get,
know.
like, a weird like.
No, why can't I?
One of them is like "why do I have strawberries in my?"
So the numbers I used here was about 56 miles an hour starting. Okay, 56 miles an hour to approximately, and whenever I make these problems, guys, I try to pick reasonable numbers. Clearly that force was not reasonable. To 23. So you're braking from 56 miles an hour down to 23 miles an hour in this problem. Okay? Alright, cool. Now how do I get off this thing? Let's see.
Would the problem change if there was like snow on the ground? Like, would you put like a problem where you like say snow's on the ground?
Sure, so it would change the amount of force that's really being applied in the end.
Oh, okay.
Yeah, here's how snow would work. If there was snow on the ground, the braking force is normally 750, it would be a less value. Because it can't, because remember it's F net we're looking at really? So because the ground would cause you to slip, the force felt would be less than the actual
The
applied.
time would be greater.
Mm-hmm. Absolutely right, Mike, yep. So with water or snow on the ground, the time would be greater for sure. What about part B? What does part B ask us to find? Yeah, very good. The distance traveled, or x. We're only moving in one direction, so displacement or distance is the same. So what formula can I use to find the distance traveled or displacement?
Vm squared equals vi squared plus 2ax. Then you can plug in ax as delta v over 2.
And then you can plug in what?
For acceleration, delta v over 2. You don't know what the acceleration is, right?
The problem is that you'd be doing a roundabout method. You'd be having your delta v's here and then another delta v over there.
Well, I mean, like, no, you're like just subtracting, like, find the acceleration.
Oh, you could find the acceleration, sure.
That's what I mean, yeah.
Yes, I'm thinking, did I do it that way?
Wait, so you're finding displacement?
Another way to do it though, to make it a little bit simpler, would be just to take the force over the mass, right? F equals ma. But that should work, the same answer. Yeah, you should get the same answer. I didn't do it that way though, but that's a good way to think about it. So what Elliot's saying here is we can find x by using this equation here. Now, if we want the acceleration, because we don't have it in this problem, we can remember Newton's law that says F equals ma. We know the net force acting on the object is F. We know the mass is m. We could solve for a here. Does that make sense? Remember Newton's second law?
Why are you replacing that with 2ax?
I'm not. I'm replacing the a. I'm going to solve for a. Solve for a up here?
Oh,
It'll be like f over m.
Yes. So we'll replace a with f over m. Because we don't have acceleration in this problem. So we'd have to take a roundabout approach.
But, for that one, would f still be negative, or would it change back to positive?
F would most definitely be negative still. Because it's a negative acceleration. It's decelerating the car. So f has got to be negative. We're solving for x. Look at the way I'm going to write this. Everybody see what I'm doing? I'm putting the 2fm all together. And then I can divide by the quantity 2f over m. Or I can multiply by the reciprocal. Remember how when we have 1/2, we always multiply by 2 to get rid of the 1/2? So in this problem now, it might be easy to do this. Just multiply by the reciprocal of this fraction on both sides.
Why don't you just write 2f? Can you do that?
Yes, I'm putting I'm just putting the symbol there just so you know it's times. That's all. But yes, you can do that. Okay? So that would be our generic solution. I'm curious, Elliot, can you do me a favor and check?
Yeah, I did.
You got a number?
Yeah.
Okay, so hold that number in the back of your mind for a sec. What do we get for it when we do it this way?
Just, I have a question.
Yeah.
Would it be the same if it was just vf squared minus vi squared over 2a, and you just hit the
And you found A? Absolutely, yeah. Yep. So Scott's saying he found A using F over M, got a number, and then plugged that number in. Yep.
So, this is like a little more complicated than that.
Then doing what he said, you mean? Or, well, what he did was he came up with a number for this F over M and just put the number in and then divided by 2 times whatever that number is. It's the same thing, really. I can divide by this parentheses here, Philip, this 2F over M, but I'm multiplying by M over 2F, which is just the reciprocal. Okay? Anybody got a number for this? Anybody got a number for this? And I actually did it a completely different way than even this in my notes, so we'll compare all 3 numbers to see.
700, yeah.
What'd you get?
700 meters.
Yeah, it turns out to be 700 meters. Okay, 700 meters.
Very effective, great.
That's what I got when I did it the other way. What do you get for this way?
700.
700 also?
Yeah.
Perfect. Just making sure. Again, both methods are true. We want to see just to make sure that the numbers actually check out. So what Elliot did was this, in case we're confused. Take a look up here. I'm going to put a box around this. Remember this was A? Elliot said, you know what? I'm just going to define this as Vf minus Vi over time. Because by definition, acceleration is change in velocity over time. So instead of using F over M, he used Vf minus Vi over time. And that works. Now, you could have also have used x equals VIT plus 1/2 AT squared. And you get the same answer also. Okay? So 3 different methods, all giving us 700 meters as our solution. Okay? 3 different methods. All right, let's take a look at the last example first. Can I get a reader, please? Can I get a reader nice and loud for this one? Joyce?
If the coefficient of kinetic friction between 2,300 kg car and a road is 0.5, then what is the minimum stopping distance for a car moving at 29
Meters per second. Okay. So 29 meters per second, that's around 65 miles an hour. A little less. Okay? So cars traveling at that road speed. The road may be a little bit wet. Maybe there's snow or water on the road. So we're given a coefficient of kinetic friction here. If we're given a coefficient of kinetic friction here, we know that we're going to have to calculate what? What are we going to have to find? Well, we have mu, but what do we have to find?
Normal force.
Normal force.
Normal force, and then get FF. We have to go through this process once again. I know. All right, so let's go through the process of this. If we can do this, it'll make it a little bit easier on us. So what's our givens for this? What's our givens, Maria?
Mu K equals 0.5, M equals 2300 joules, Di equals 29 meters per second, and Df equals 0.
Well done. Okay, and what are we looking for? What are we looking for? The minimum distance, so x. Okay, we're looking for this x value here. Now, clearly the momentum impulse theory is not going to give me a solution for x, because there's no x involved in the momentum impulse theory. But the momentum impulse theory can give me the force applied. If I have the force applied, I can then go ahead and find the time it takes. So let's take a look. So if we have momentum impulse theory, it tells us that delta P equals F times T. If I know what the delta P value is, how can I figure out delta P in this problem?
And negative MVI,
Because
because Vf is 0.
Vf is 0, good. So let's drop this off. We get negative MVI equals F times T. What kind of a force is acting on this object? Kinetic friction, very good. So to get friction, we have to do mu times mu times what? Fn. But Fn is really mg, very good. So this is really mu k Fn. But remember, normal force on an object that's in vertical equilibrium is equal to its weight. Again, if I slide this remote back and forth, the normal force acting up is equal to the weight acting down because I'm not pulling up or down. So the car is like sliding this remote back and forth. The car is not floating off the ground. There's nothing pulling up on the car. So the normal force is indeed its weight, Fg, but as Reese said, Fg is just mg. So here's what we've got now. What do you notice? Yeah. So we didn't need this in the problem. Maybe we'll need it later, but for now we don't. Okay? We don't have time. That's the only thing missing. So why don't we solve for time? We've got VI. We've got G. Let's go ahead and solve for our time.
Why'd you get rid of the friction?
Oh, thank you. Thanks, Ev. Okay, so we've got time equals negative VI over mu G. Over mu G. And this is where it's going to get a little bit confusing. Because when we studied forces, we always said, let's let G be positive. When we did kinematics, we had G be negative here. This is one of our situations where G actually is negative, because this is kinematics. We're now looking at equations of motion here and not forces anymore. So G is negative 9.81.
That makes sense, right? Because it's time.
Yeah, because we're looking for time, and time has to become positive. Yeah. Grace,
I got 6 seconds, 5.9.
you see what I got? I didn't even come up with a number. I left it in this terms because we're going to use that in a minute. But that works. Others get that number?
Yeah.
Yeah? All right. Now, but that's not what the problem asked for. What did the problem ask for? The displacement or distance, right? So what should we do? Let's go back to what we did in the last problem. But you know what? I'm going to use x equals VIT for this one. Is that okay? It's the same answer as we got earlier. If we did it with VF squared equals VI squared plus 2AX. But I'm going to use this because it's already solved for x. And I'm looking for x. So why not use it, right? This is what I did, by the way. I replaced time here and here with this expression. That's what I replaced time with in these two spots. I replaced it with that expression. But the number works just as well, right? What is the acceleration?
You know, like last problem or before, where Elliot replaced it.
Yeah, so we're going to want to use the VF minus VI over T because we don't have a force in this problem, right? We never got the force. So we can't use force over mass. Remember last problem we used force over mass from Newton's second law to replace acceleration? We don't have an actual number for the force. So it's not useful to use the force here. Yeah, use the force, Star Wars. Anyway, but we should use delta V over time. Okay, and I should replace those because I'm replacing everything in one line.
Wait, why did you change that to
Because I replaced it, I wanted to do the substitutions all at once. What do you end up getting for a number here? I really encourage all of you to be doing this. You get much better using your calculator, you get faster on the test. It really helps you. 85.55? Yes? Check. Okay, it should be around 85 point something, I know that. 85.6 we'll say to round. 85.6 and our units of meters because we're looking for the displacement. Now, I need to mention one thing. On a midterm, you can choose to solve this problem by using the word kinetic energy theorem and it might be a lot easier. You don't have to use momentum impulse. This is a very complex problem. I'm probably not going to give you a problem this complex on your test. I'll tell you that now. I wanted you to see this because it could also be solved using the word kinetic energy theorem. So this kind of a problem can definitely exist on your midterm exam, but I would not recommend using momentum impulse theory. I would use W equals delta KE. Okay, and what that would look like would be this, just to give you a little heads up. Well, this is D, right? Okay? And if you solve this whole problem generically, you would get the exact same answer as here. Okay? Cosine of theta, remember, is cosine of 180. That's the only difference there. Don't forget, you guys, from this section, it's right here. Okay?